In lab, you guys were looking at what happened when states of matter changed. You looked at how the temperature changed when water changed from solid to liquid, liquid to gas, and from liquid back into solid. Those are all phase changes. And what you noticed, or what you hopefully noticed, was that the temperature actually remained fairly constant while the phase change was occurring. And that gets back into thermal energy and the two kinds of energy that are involved. There's forces of attractions between particles. And remember, when you have forces of attraction, you can have instability because forces of attraction want to pull things together. And that means they're going to try to move particles that are apart together and increase their stability. So in order to get a phase change to occur, we either have to add energy to increase the instability and move these particles apart, or release energy to increase the stability and move the particles together. But while that particle rearrangement is actually changing, the energy is a potential energy change, not a kinetic energy change, so the temperature remains constant during the phase change. So if you think about it, the particles, when they're all lined up in a solid, they have very, very little potential energy because this is a very stable way for them to be. They're all in their spots. None of them can go anywhere. There's strong forces of attraction holding everything together. That's very, very stable. As I add energy to that, though, if I make this more energy and more energy and more energy, that's a metal fire, I'm adding heat to it, then eventually what we get are these particles that start to fly off of this. Okay? This moves around. This becomes less organized. And that means we've made it unstable. We've taken energy and we've made this unstable. We've increased its potential energy now. These particles have more potential energy because they have the potential to return back into this solid state. That energy did not go into making them move faster. It just went into rearranging them. That's why the temperature remains the same during the phase change. So let's take a look at this. There's two kinds of phase changes. There's endothermic phase changes, which absorb energy. Now think about that. If particles absorb energy, they go from being more ordered to less ordered, right? They go from being stable to less stable. So a solid becomes a liquid, and that becomes a mess, right? We don't have order anymore because these are jumbled all around. Okay, so that took energy in, and that can go one more step, and that can go to a gas. That made them even more unstable. Now they're bouncing around all over the place. That required energy. To make these things less stable required energy. So these are endothermic phase changes. When a solid becomes a liquid, we call that melting. It took energy. When a liquid becomes a gas, we call that vaporizing or boiling. That takes energy. And then you can actually skip that middle step and you can go from a solid directly to a gas. It still takes energy. That's called sublimation. This is a curve that shows us how temperature changes with time if we're adding energy to a solid. And so we add solid, the temperature increases until the particles gain enough energy that they start to rearrange. And then the energy we put into it starts to make those particles change their positions instead of speed up. And then we hit the liquid phase and the temperature starts to go up again because now these particles can gain more energy and move more and move more and move more. But this will plateau again until it vaporizes. So here we have boiling, and then it'll turn into a gas. So this curve continues like that. And we did see that in lab. Now if these phase changes happen in reverse, we get what are called exothermic phase change. Exo means exit, to leave. Thermic is referring to energy. Okay, so this means we're going to have thermal energy being lost. Now think about that. If these particles are bouncing around all over the place, they're gas, they lose thermal energy. That means they're going to become more stable. They're going to change into a liquid. And if they lose even more energy, they can become more stable and turn into a solid. So potential energy is lost in a phase change, in an exothermic phase change, because they're becoming more and more and more stable. And we have three exothermic phase changes. When a gas turns into a liquid, that's called condensation. It condenses. When a liquid turns into a solid, that's freezing. And you can skip the middle stage and you can have deposition, which happens when a gas goes directly to a solid. And that's how frost forms on your windows in the wintertime. That's deposition. Water vapor in the air turns directly into a solid. Now, These three phase changes, if we put them all together and we show you these graphs, we have solid to liquid to gas, energy temperatures increasing, energies increasing. This is the energy of those particles. All of these are endothermic because we have to put energy into it to make these changes happen. But if they're releasing this thermal energy and they're becoming more stable, then this is exothermic because we're releasing energy to the atmosphere. These particles are losing energy to their surroundings. I do want to show you one more thing. We can draw what I like to call the phase change triangle. And in the phase change triangle, we just put every state of matter somewhere. It doesn't matter where. We're going to put solid up at the top just because we can. I'm going to put gas over here in the bottom left, and I'm going to put liquid over here in the bottom right. And then we're going to label each phase change and decide if it's endothermic or exothermic. So we can have a liquid go to a gas, and we can have a gas go to a liquid. Every phase change has its opposite. We can have a gas turn into a solid, or we can have a solid turn into a gas, and we can have a solid turn to a liquid, or a liquid turn to a solid. So let's start right here with this gas becoming a liquid. That's not a very common phase, that's a pretty common phase change. Anytime you have condensation on the outside of your cup, or you have dew on the grass in the morning, that is condensation. That is a very, very, very common thing that happens. What kind of phase change is it? Is it endothermic or exothermic? Well, gas has particles bouncing all over the place. That's unstable. Liquids, they're together. That's more stable. That means in order to go from a gas to a liquid, you had to lose energy. So this is exothermic. Energy exits a gas and we get a liquid. Of course, the opposite then, a liquid becoming a gas, that's boiling or vaporization. And that happens when energy is gained. So this is endothermic. We can go next to this side. Liquid becomes a solid. That means we went from motion and fluid movement to rigid, no moving. Everything's locked in position. That means it gained stability. It became more ordered, so it had to lose energy to do that. So freezing, liquid to solid, freezing is exothermic. Okay. Melting then, when a solid becomes a liquid, we went from ordered to less ordered. We went from stable to less stable. That takes energy. This is endothermic. Then we have gas to solid. Okay, if a gas becomes a solid, why don't we reverse these two arrows? And so instead of looking at a gas becoming a solid, I'm going to look at a solid becoming a gas. Okay. And when a solid becomes a gas, we go from rigid particles locked in position to particles that have become very disordered and have lots of potential to fall back into a solid. So this is sublimation. Dry ice sublimates. It skips the liquid phase. It goes directly to a gas. That's why it's called dry ice. And this is endothermic. But then the opposite of that, gas to solid, when a gas loses all its energy and turns into a solid, that's exothermic. And this is called deposition. And you can think of that as deposit, when gas deposits as a solid.